start in 15 minutes. 10:15 local time. Nobody home. 1 minute. We will start in 1 minute. Last lecture in this season, this semester. What I'm planning for today is one of the photo occasion techniques. For example, you have ground and underground cable with a fault somewhere in ground. How to find a fault place? It's a large question because digging all the trace is very expensive. One of the techniques used called reflectometry. And it's based on circuit theory. Let's say I have a line. If I can take my special magnifying glass, very small piece of my line can be represented with capacity to ground this will be very small piece of my line. The X will be ground capacity, inductance, small differential of resistance, then yeah, maybe it's worth to draw it here. Insulation resistance G, and again ground capacitance. Next one, here is my very small piece of line length. Such line can be described with so-called telegraph equation. So-called telegraph equation partial differential of voltage by distance and time divided by differential by length, distance, equals to L1 current as a function of distance and plus L1 current as partial differential from time. Here, L1 is a resistance capacitance of 1 unit of length. This is equation number 1. Equation number 2. Two equations. Second equation is partial difference by length of current equals to G1 voltage as a function of distance and time plus C1 partial derivative of voltage by time. This is second equation. Here, G1 is an insulation conductivity of 1 unit of length, 1 meter, 1 kilometer, 1 mile, not important. And C1 is capacitance of 1 unit of length. Solution of telegraph equation system brings us wave equation. Voltage as a function of distance and time will be first function minus x divided by v plus second function plus x divided by v, where x is a distance, t time, and v is a propagation speed. Speed of propagation 1 divided by square root of L1 C1. It's a speed of wave propagation. Here, function f1 shown in function f2, what they are. f1 is a function of direct wave. We analyze what happens in line in form of direct wave or falling wave. This is wave propagating from the power, from our source. And f2 is backward going wave or returning wave in our line. Current here can be presented as, of course, a function of distance and time. X is a distance, t time, so it will be direct wave or falling wave plus backward going wave this is equation for current. Again, I will repeat, phi1 is a wave going forward, phi2 backward or returning wave. In any point of line, value of direct wave equals to square root f1 c1 phi1 minus x divided by v, because Ohm law is still in charge here, should be obeyed. Time plus x divided by propagation speed. This is true in any point of line. We can write what? In any point of line, it's a voltage at sending point and current at sending point, equals minus its receiving point equals to line, so-called line characteristic resistance. Line characteristic resistance equals to square root of 1 unit inductance divided by 1 unit of length capacity. Now, since we have differential equation, we need to deal with them. Let's take let's take all this into Laplacian space. So let's now go to Laplacian representation. We immediately can see one problem. Our first equation do not meet the Reflectometry condition. To make it comply with the Reflectometry convenance, we need to multiply it by e times power t, and to get how to say easier or more common form, we should integrate it in time, or we will waste our time. So what we will get? We will get derivative of voltage by distance p by distance. Laplace transform eliminates time but do not eliminate distance. Distance remains. Will be L1 plus PA1 current no distance and complex frequency minus a current at 0. This is current at 0 time or initial condition. This is equation number 1. Equation number 2, we will obtain, will be derivative of current by distance equals to insulation conductivity plus insulation conductivity of 1 unit of length plus capacitance 1 unit of length, voltage as a function of distance and complex frequency minus C1 x0. It's a 0 time charge of the line. Charge before. Here it's okay to use 0 starting condition. It's not okay if we try to catch live wave of the initial fault. But here we operate on already faulted line, so there is no problem assuming what voltage at is 0 and current 0 is 0, so line is not energized before. We write following. Equals to minus current no current of divided, not divided by derived, sorry, equals 1 from P voltage here L1 plus PL1 longitudinal resistance of one length unit. This one is G1 plus PC1. Insulation conductivity plus capacity to ground. This equation has the same form as original telegraph equation. Solution for such kind of equation known in form of hypertrigonometric function. So I can use known form of solution equal P at power x plus f power x, and current can be A divided by characteristic resistance f power gamma x mean divided by characteristic resistance. Again, it will be function of complex frequency f power gamma x. A and B are defined by initial conditions at line ends. These two, A and B, are dependent or calculated as a function of initial conditions on line end. Gamma is a propagation factor. While A and B are determined by initial conditions, gamma being square root P propagation factor is a function of line parameters. Wave resistance, here it will be a function of complex frequency divided by one wave resistance. Assuming that current and voltage will have their image in Laplacian space, we can write voltage as a function of distance and complex frequency. Receiving end voltage, receiving end current, divided by half, multiplied by a power minus propagation factor minus n plus receiving and current divided by 2 f power gamma x minus L. It's equation number 1. Here, equation number 1. Exists equation number 2. Equation number 2 is current in line. It will be receiving end voltage plus receiving end current, characteristic wave resistance here f power minus gamma x minus L minus voltage minus current multiplied by wave resistance divided by double wave resistance f power gamma propagation factor minus A. To simplify, notation, hyperbolic functions are used. So, voltage is image of the voltage receiving and hyperbolic cosine of gamma xi plus current at receiving and wave resistance hyperbolic sine of gamma xi. Current can be written as hyperbolic cosine of gamma xi plus sec divided by hyperbolic sine of gamma xi. Who is xi? Xi denotes L minus x. Two nice equations. Easiest mode is when a line is loaded with resistance equal to its wave resistance. So when a line is loaded with equals to in this case equals to f power f power minus gamma x equals to sending end voltage at power gamma x. Current will be second image of secondary voltage divided by wave resistance at power gamma x. This is equal to sending end voltage divided by wave resistance at power gamma x. If we omit losses, assume that losses are negligible. If we omit energy losses, will be 1 from P a power minus x divided by V P. I need to remember what propagation speed is 1 divided by square root L1 C1. This means that propagation factor will be P square root L1 C1. So what we will see? We will see propagating wave. Propagating wave 1 minus x divided by V, and current will be sending current minus x divided by propagation speed. Easiest mode when a line is loaded with resistance equal to its wave resistance. If not, what we will see? We will see forward wave of or falling wave, as power propagation factor as a function of complex frequency. Simple schematics. Let's say I have here is kind of internal resistance switch, and here goes my line with the length of L. Line is loaded with some resistance through the line will propagate with the speed of v wave. What I need to write? I will see was at the point, how to say, connection point. In initial moment, I will see something like this. What will happen? Wave propagates, 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 reaches the end of the line. At the moment x equal to a, propagating wave reaches the end of the line, and something will go backward. Falling or direct wave is what I'm writing, block, 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 I'm writing as a function of p plus p divided by half. Backward going wave or reflected wave. This one is forward, or better call it falling wave. Reflected wave or return will be divided by 2 or p sorry, this is mistake, divided by half. This is written at the line end point. Reflection factor or reflection ratio divided by now returning wave reflect reflection factor UF F power propagation factor this equals to again reflection factor F power minus 2 propagation factor A a power propagation x. At the moment returning wave reaches the starting point of 0 meter of the line, reach sending end, it again will reflect. With reflection factor internal resistance minus line wave resistance. This is internal resistance. Internal resistance plus line wave resistance. So this second returning wave will be first reflection ratio, second reflection ratio, one multiplied by A, power minus double propagation factor A power minus propagation factor X. Now, what we will see? I'll be back in a minute. What we see? From 0 time up to A divided by V, moment when following wave. Hi, Lucia, how are you? Thank you, I'm fine. So, at the moment, till the forward wave, initial wave, reach end of the line. we will see propagating power propagation factor. At first moment, initial wave goes forward till it reaches the end of line. Then it reflects from the end of the line double A divided by V. It goes backward and we see this. Multiplied by A power minus propagation factor x plus reflection factor at the end of the line multiplied by A power minus gamma double A minus x. First stage, initial wave goes through line. Second stage, wave returns. Third stage, when returning wave reaches the sending end of the line. It will happen, okay, divided by V time length divided by propagation speed. For this period of time, one, two, three, we see what? A power minus gamma x plus reflection at the receiving end double A minus x plus multiplied by A power minus propagation factor double N plus x third wave. To explain this, I will take simple example. Let's say I have kind of E0, it will switch on to my line and line of length and here is infinite. Open line. In this case, reflection for this end will be 1 and reflection for this end will be -1. Well, this one. Sending voltage, simple, A0 divided by will see first wave goes forward 0 time until it reaches the end. First stage, what we will see? One image of U1 at power x. So here we will see 0 divided by p at power minus px divided by propagation speed. This wave goes forward, reaches end of line, nothing's there, and all energy returns back after first reflection. Time double A divided by V. Second voltage will be E0 divided by P multiplied by A power minus gamma x plus A power minus, here should be gamma, double A plus x. This is second, first reflection. One more reflection from sending end. Divided by propagation speed, time divided by propagation speed. We have reflection from sending end. Here our voltage will be E0 divided by complex frequency at power minus gamma x plus A power minus gamma double A minus x minus A power minus gamma double A plus x. Now I need to get it in some form of time function. To do so, I need to implement delay theorem from the Laplacian transform. Allow me to, this is 1 minus x divided by v. So here, for the first stage, it will be divided by x divided by v, or E0 multiplied by switch on function t minus x divided by v. For the second stage, I will get E0 multiplied by switch on function t minus x divided by v plus switch on function t plus double a divided by v, where v is propagation speed and line length. For the stage number 3, it will be E0 multiplied by 1 minus x divided by v plus 1 plus double a divided by v and minus 1 t minus x plus double a divided by v. Okay. Look what will happen. Okay. This way goes x. For the first stage, wave propagates with the speed v. Its magnitude is a0. Voltage as a function okay. Simple x, I don't have time. Voltage as function of x. Stage number 1. Wave propagates forward. Stage number 2. One second, I will draw stage number 2. At stage number 2, we will see this thing. Backward propagates waves with the speed of v, double E0. This one is E0. This is what happens at stage number 2. Double voltage wave propagates backward. At stage number 3, why I'm drawing this? Because wave with the magnitude minus E0 propagates from the starting point here, double E0, For observer, wave from double E to single E, zero propagates. This is stage 3. If someone takes a look at the end of the line, he will see something like this. It's a time chart at the end of the line. A divided by V, triple A divided by V, 5A divided by V. Nothing, nothing, nothing. Op double E 0. Nothing, nothing, nothing against double E 0. Okay, fine. What I got here is a model of line with distributed parameters. Here are coils and capacitance for each small piece of line length. Here is my signal generator. It's now set to 0.2 microsecond pulse. Oh, okay. Come on. Oh. Yellow line is ascending end of my line. This one is ascending end of my line. One moment. Need to blue line is receiving end of my line. At this moment, line is loaded with its wave resistance. At this moment, it's aligned line. So, line, no, my finger is not necessary. Line is loaded with its wave resistance. As you see, no reflection. Wave goes forward, wave arrives. This is propagation time. Now, what will happen if I open my line? Oh. Here, line is opened. What do we see? Loaded with wave resistance. Line loaded with wave resistance. Line and opened. See what happens? Pulse arrives, reflects with minus sign, and here See this one? It's a moment when double my line is with losses. It's moment when pulse returns. So here pulse returns. Oh, so it's later it's all delays. Next reflection. My line isn't lossless. That's why we see decay. So here what happens at open line? I'm sending pulse. Here pulse returns with positive polarity. Okay, it's an interrupted line. What will happen in case of short circuit? What will happen with for this case? Reflection factor is -1. To make it into scale. In case of longer pulse, no, longer pulse is not here. In case of long pulse, not so here very visible. He's returning forward one. Here, double E returns. Reaches the end. I took a longer pulse. Voltage at sending end. Here, moment when returning wave arrives. So this time period gives me length of the line or distance till interruption point. In case of here line loaded with its characteristic resistance, no one returns. Here. Pulse go, pulse arrives, here returning. Okay, I like to tackle short circuit. For this case, it's better to write currents. So, for the first stage, divided by V. For the first stage, current will be something like 0 plus switch on function T minus x divided by V. Direct wave will go forward. Where is my plug? I'm talking about this mode. For the second, period, we will see E0 multiplied by 1 minus x divided by V plus 1 plus x minus double A divided by V. And it's first reflection from, how to say, receiving end, and for third one come on, switch off. And for the third I will see something like 0, 1 plus minus x divided by V plus 1 plus double A divided by V plus 1 minus x plus double A divided by V. 1, 2, 3. What happens? If we control current, for the first stage, we see what? Propagating wave of rising current, I0. For the second stage, we see backward wave of decreasing, double E0 to this is I0. It's a second stage, and at the third stage, 1, 2, 3. This one will be triple E0. Wave goes this. For voltages, this is for stage 3. For voltages, propagates. For the stage 2, backward propagates wave with magnitude minus E0. We see it as a dropping voltage. For the stage 3, this is stage 2. At the stage 3, wave with magnitude double E0 goes forward. And this one is minus E0. This wave goes forward with the wave. In general, if resistance at the end is greater than line wave resistance, we see positive reflection. If less, negative. Here, short circuit AMF. Here for the short pulse, here arrives minus E0. Here arrives plus. If plus, see, then returning, this one is double propagation type of line. This gives me, look what I can do. I take healthy phase. With the short pulse, here with the short pulse, time of return. This time space gives me line length in measurement units. Now I go to 40. This gives me distance to 40. One moment. I have, oh, here, come here. Come here. Here, I'm imitating fold at the middle of the line. See? Fold in the middle of the line. Fold at the end of the line. Negative wave. This one. Open line. Fold at 50%. So I can calculate distance to the fold. Yeah. Where am I? Here. I have this network model. It consists one line, a bus, and two secondary lines. being sent. I'm setting yellow line is on the first percent of my line. And my blue, oh, come here. Oh, here he is. It's different time scale, sorry. Oh! Sorry, I didn't switch time scale. Now, first line is open, yellow line is sending end, blue line passes at the end of my system. One moment. Here is my line, and at this bus, at this moment, all disconnected. Sending pulse. Where is my yellow? Here I'm taking S1, and at this point S2. What can I imitate? To illustrate here. What happens when line is loaded with its wave resistance? It's pure for theory. Nothing reflects. Line opened, fault at the end of the line. Line opened, line short at the end. See? This is return, line open interruption, fault. In case, here, for example, fault at 50%. Here, line short circuit at its end. Now I can have plugged the switch on, and I have attached second line. Oh, here second line is open. Short circuit fault at the end of the second line. Bus with the okay, here open fault at second line, fault at short circuit at the end of second line. Just to illustrate, 60% of second line. Again, you see, but why I have to learn? What if I connect this line? Now my life will be not so easy. Here I have two lines. To illustrate, short circuit, these lines are two upper line have the same wave resistance. Lower line has 2 times more wave resistance. Look what happens. Short circuit at the end of the second line. Short circuit at the end of the third line. who is this? It's a reflection from the junction point. At the junction point, I have parallel wave resistance. When both switches are on, wave resistance of this line are switched in parallel. At this point, I have a transient with reflection factor for lowering resistance. So, here is this wave returns from the junction point. This wave returns from the end of the second line, and this wave returns from the end of the third line. If I have fold 50% of the fold in this point. As you can see, while I operate on single line, it's not so problematic, so I see a clear picture. But problem what I to see reflection from any non-uniformity of my line. If I have something like T connections, underground T connections, it's easy when I can measure from this point. But if I have buried connections, it's often used in city network, where tie connection to transformer. This one goes to a transformer. This connection will make my task. I should be very skilled. And what I can do, I can send someone to this transformer points to make artificial shot here at fuse connections. This will allow me to see. I'm short circuiting my short line. I can tell which reflection is from the fold. Here, situation. Fold at the 60% of the second line, and I'm making artificial fold at the end of the third line. I'm simply sending someone with earthing link, do it. Otherwise, because junction is not if junction, this bus point isn't available, I can't tell anything. Of course, it's much better to disconnect here. Ideal pure fold at 50% of first line. Much easier. Healthy. Healthy system, but this is reflection from junction point from buses. fold at the end of the second line, for 2 folds, both at the end of the second and at the end of the third line. Have open. Okay, you solve. You solve this. It's required train time. On this point, I'm finishing my course. I used my time, so I'm officially declaring this course ended. Thank you for your attention. Lecture. Course of lecture. But
yeah.